Okay, today we're going to get into this section where we now want to use Monte Carlo methods for. So we spent a lot of time talking about generating random numbers or sampling from a distribution, okay? And now we can start applying these things. And so now we have Monte Carlo methods for, kind of estimating expectations. Okay, expectations being kind of like the mean of a distribution or the mean of a, the expectation of a function, something like that, okay? Or, the mean of a function over a distribution. Okay. So Monte Carlo methods for estimating expectations, and this is based very heavily on Chapter 3 in the textbook. Okay, Monte Carlo integration, importance, sampling, all of that. Okay, so this is Chapter 3 from Robert and Casella. Yes.
In regards to our midterm material, what day is the last day that would be?
I would say Monday. Okay, so I won't put this stuff on the midterm. Okay, and I'll talk a little bit more about the midterm on Friday. All right, so let's say. So we'll start off with Monte Carlo integration, okay? And so let's say we have a function h of x, okay? And we want to compute the integral over h of x, okay? I want to compute the value of a definite integral. Over from a to b. So we want to know, and we're just going to call this the value I. Don't get this mixed up with the identity matrix or anything. We're just going to say we want this value I, which is the value of the integral from a to b of h of x dx. Okay, and this function h of x could be complex, and we might not be able to solve it. Okay, so h of x could be difficult to solve analytically, or there, we might say there's no closed form solution or something like that. Okay. And so we can say, if we're going to do Monte Carlo integration, we can say that the average value over the integral, okay, the average value of the function over the integral, over the interval is you do, the difference, the width of the interval, okay, basically calculate the integral from a to b and divide by the width of the interval. Okay. And so we can say this is the expected value h of x, or maybe I'll put square brackets around to kind of differentiate. So this would be the expected value of the function over the interval. Okay, and here, and so this is just the average value of the function over that interval. Okay. And this one puts basically, if we weight all values of x the same, okay, which is the same, we would say this is uniform weight, and we would say x comes from the uniform distribution. Uniform from A to B. Okay, so this is how we can get the kind of the expected value of the function itself over that interval. All right, so if we want to do this, all right, without having to actually compute this this integral, we can just do this the Monte Carlo way to solve this problem. Okay. So let me just kind of say this is what we want, right? So so the Monte Carlo method to estimate this value. Okay, and so the Monte Carlo estimate of this thing we will call h sub n bar. Okay, so this is h sub n bar. This is the or h bar sub n, I don't know, h sub n bar. This is the Monte Carlo estimate of the expected value of the function. All right, and so all we have to do is generate a bunch of x's. And so we will say x super 1, x super 2, all the way up through x super n. So this is just generate n values coming, IID from uniform A to B. So just generate a whole bunch of x's. Generate a bunch of x's, and then number 2, evaluate the function at each of these generated x's. Okay, so you evaluate h of x okay, so just evaluate the function at these sampled locations. And then calculate the mean of these values. Okay? Find the sample mean of these values. So that's basically just, we'd say h sub n. Basically, we just add up all of these h's, h of x to the I, from I equals 1 to n. We add all of those up, and then we divide by n. Okay, so this is just draw random values, evaluate the function at those random values, take the mean of those things. Okay, and then if we want to get back the, so this is the mean of these things. If we want to get back the value of I, okay, well, I is technically this divided by b minus a, right, the expected value of h of x. So we can estimate I by taking this and multiplying it back by b minus a. Okay, and then so now we can get an estimate of the value of the integral by multiplying our estimate of this by b minus a. Okay, so we just say I hat, so this is our estimate of the integral based on n samples. Which are right. All right. Is this okay? So let me just demo this. Maybe this is a silly demo. I didn't even bother coding it up ahead of time because it's okay. So let's say just our function. Let's say our function is function of x is just x. Okay. So if I and let's just go from, so let's just say h of x is just equal to x, right? And then so we have this. Okay, and then we want to know, okay, what's the average value across, let's go from, let's say 0 to 2, right? So we can integrate x dx from 0 to 2, right? And then so if we wanted to do this, we would have to do x squared over 2 from 0 to 2, and then we would just get what? What's wrong with me? So 2 minus 0, and then we would divide this by the distance over 2, and we would get the average 1, right? Did I mess something up? Wait, I'm always
4 minus 0.
4 minus 0. What am I doing? I hate doing integration in real life because right, so I get x squared over 2, right? So I get 4 over 2, okay, minus 0, right? And then okay, so this gives me 2, but then I divide by, oh, okay, well no, okay, this is the I. This is the I that I want, okay? And then yeah, see, I'm getting myself all mixed up. And then we would calculate, to estimate this thing, we would calculate the average of these things, right? So we want h bar sub n, which is going to be, we're just going to sample, right? We're going to sample a bunch of x's. Okay, and then we evaluate the function at x, which is not exciting, it's just x itself. Okay, so evaluate h of x. Okay, and then we take the mean of these things. Okay, and so if we take a bunch of samples from 0 to 2 and I calculate the mean, we're going to get what? Something close to 1, right? And then so that would be this quantity, and then we multiply it back by the width of the interval, and then we would get back the value of the integral. Okay, so So we'll say, you know, our x's, we'll just do r unit, I don't know, 1,000 values from 0 to 2, okay? And then we can say evaluate h of x, so this is exactly going to be h of x, okay, as x itself, and then we calculate the mean of all of these things, okay? All right, so this is the mean of those 1,000 values that I've drawn, okay? So my h sub n here is this, and then I just, to get back my estimate of I take this mean, and I would multiply it times b minus a, which is going to be 2 minus 0, right? And so my estimate of the integral after 1,000 samples is 1.88. Okay, it's not perfect, but all we had to do was just draw a bunch of samples. Okay, and then so, you know, mathematically we can demonstrate that these indeed they give us good, I guess, properties. So properties of the Monte Carlo estimate h sub n bar. Okay, so the expected value of this thing, so this in of itself is an estimate. Okay, so just keep in mind that this in of itself is an estimate of the function here. Okay, and so the expected value of this, so the expected value of the estimate itself is, okay, we can say, well, this is going to be the expected value of, you know, its definition, which is 1 over n times basically the sum of at h evaluated at our random samples and this becomes 1 over n times the expected value I'm sorry, not the sum of the expected values and so this ends up just being the expected value of h of x. Okay, so this we would say is an unbiased estimator. Meaning that in the long run, this thing is expected to be equal to this thing. Okay, but of course, based on any given set of samples, maybe it's going to be off by a little bit. But and as far as the variance goes, the variance of our estimator here, I'm just going to kind of skip ahead to the end, just ends up being 1 over n times the variance of the actual function. Okay, and because this thing is an unbiased estimator, then that means, so because this is an unbiased estimator, then our estimate of I hat sub n is also an unbiased estimator of the value of the integral itself. The integral itself. Okay, and then the variance of of our estimate of the integral, okay, ends up being kind of the variance of I, which is the variance of b minus a times h bar sub n. And so this, we pull this out and we get b minus a squared times the variance of this thing, which becomes 1 over n variance of h of x. All right, is this all good? Just a little, yeah, question?
Oh, sorry, I was just wondering about the variance, the original variance of h bar sub n.
Oh, this one? How we got this O to be 1 over n? Yeah, I kind of skipped over that. Sure. Let's here. I guess we can do a. Wasn't sure if we were actually interested in how all of this got. So h bar sub n is 1 over n times the sum of h evaluated at each of our sampled x's. Okay, and so as we draw a bunch of these things, we can kind of pull out. So this is just a constant. So I can pull this out of the variance, and we're going to get 1 over n squared times the variance of basically h sub x at all of these. I'm sorry, I left out my summation of h sub x over all of these things. Okay, and then so this becomes no. Okay, so sorry, I keep messing up here. Delete. Variance, so I'm going to pull out the 1 over n squared, okay, and then it's the summation of the variances. I'm sorry. Yeah. Okay, and then we've got n of these, so we've got 1 over n squared, and then the variances of all of these different things is going to be n times the variance of h of x. And so these n's cancel, and then we get 1 over n in terms of variance. Of h sub x. So that's how we get this one in the first place. Okay. Okay, so let's we'll just try it with a slightly more complicated example here. Okay, so the function, we'll say h of x. The function h of x will be cosine 50x plus sine of 20x, and we will square this quantity. All right, so what does this thing look like? Okay, and we'll go over the from 0 to 1. So this will be our function. So in R, we've done this. So we're going to do function cosine 50x plus sine 20x quantity squared. That's going to be our h of x. And you can plot this. You can say, draw a curve h of x from, n is equal to 1,000. LAS is just kind of the alignment along here. Or wait, no. Yes. So, if I plot this, this is what the curve looks like. Or if you wanted to say, I don't know, t is a sequence from 0 to 1, and we'll say bi is equal to 0.001. Okay, and then we can say plot t versus h of t, type equals L. We get pretty much the same thing, right? Okay, and then so the Monte Carlo integration part, set a seed. I'm going to just say we'll draw 10,000 samples, and I'm going to say x. We're going to just draw 10,000 samples from the uniform 0, 0, 1. I think I can do rug of x. It's too many here. Rug works better if you only have like 50. Okay, so if I do, let me redraw this. Okay, so these are the kind of the 50 locations that I've sampled here. Okay, and then we would evaluate the mean of those, evaluate the function at those 50 sampled locations, and then we would calculate the mean of that. Okay, and that's based off of 50. But probably we should do something like a lot more than that. And I won't draw the rug here, and then we'll calculate the mean. And the mean ends up being, well, it wasn't too terribly different from the estimate based on 50. Okay. And we can kind of take a look and see how this thing has worked out if I just take my h sub x and I kind of do a cumulative mean, okay? Or I'm sorry, instead of having to like redo a loop over and over again, I can take advantage of the cumulative mean, okay, right? And what we're going to do here is I can just take the beginning of, so if I just say, what were the first, kind of 6 values here, and I can say, what were the first 6 values of the function at each of these locations, we can just do a cumulative sum of these things, right? And so basically it's going to just if I just take the head here, it's just going to take this and then add this, and so the cumulative mean will be, this divided by 1, this next value, which is these 2 together divided by 2, and this one, which is these 3 added together divided by 3, and so on and so forth. So I would just do this, and I can do the cumulative sum, and so let me just, the length of the cumulative sum is 10,000, so there's 10,000 entries for a cumulative sum, and I can just divide this by basically 1 through 10,000. And we'll store this as h bar n, okay? And so now h bar n has 10,000 entries in it, and I can kind of just I can plot n versus h bar n. Did that? Oh, I'm sorry, 1 through n of this. Okay, and so we can see, in the beginning there's quite a bit of you know, a little bit of wiggle, and then starting around here it gets quite steady. Okay, so you know, if I ran this whole thing again, our thing would probably be different, but it would probably steady out around here as well. And we can, you know, kind of create some bounds by looking at the variance, right? So we can create the variance of m, which estimate the variance h sub n bar, or h bar n, okay, sub n. And so this will be the function, and what we want to do here is we're going to kind of just calculate basically like a sample sample variance estimate here. So we would take each of those values, h sub x from 1 through m, okay? So this will be, you know, like the first 10 values, okay? And then I would subtract off the mean of those 10 values, which is this, right? So this is the difference between the first m values and the mean of those m values, okay? And then I would square those differences, and then take the mean of those squared differences, right? So so I could do the mean of this, and then I would then divide by 1 over m, right? So 1 over m times the, let's see, does this kind of make sense what's going on here? So we said the variance is, you know, 1 over n times, so here I'm doing kind of the average squared distance from the sample mean, and then because of this thing, we're going to do 1 over n. Okay, so this is what we have, and so I'll calculate the variance for each thing. So we'll get a running estimate of the variances. So I'll v sub n, and we're going to apply I'm going to just 1 through n, and we're going to apply the function, the variances of m. Okay, and then the standard error will be so this will be kind of like the running variance, and this will be the running standard error. Okay, so I hope this works. And so we'll plot this, and then we'll add kind of some boundaries here, right? So here's my plot. Let's add lines h bar n bar to n minus, we'll just do a 1.96 times s sub n, and we'll say color is equal to blue. Okay, so that's the lower bound. Well, I don't know if this will work with the upper bound. Okay, so we get something that shows, you know, creating kind of a confidence bound, and as the number of samples increases, it steadies out, and this our confidence band gets smaller and smaller. Yes. So it's the function. So basically, what I have is, so h sub x is kind of like the function h evaluated at a whole bunch of different x locations, right? And rather than having to just like go through a loop where I'm saying like first do it for the first one and then do it for the next first two and then the first three and the first four, we can take advantage of kind of these cumulative functions. And so for the variance, the m is just kind of a placeholder saying like if m is 5, it's going to do it for the first 5. If m is 10, it's going to do it for the first 10. And so what I'm saying is take subset h sub x, the first from 1 through m. So like let's say m is 10. So this is going to take just the first 10 values in that vector h sub x, or h of x, okay? And then from there, we're going to subtract off the sample mean of those 10 values, which we've already done. The calculations for us have already been done by using the cumulative sum divided by 1 through n. So this is, take the first 10 values in that vector. From each of those 10 values, subtract off the sample mean of those 10 values. And then take that difference from the mean and square it, and then take the average of those. So that's kind of the definition of the variance, right? And then we're going to multiply that by 1 over m because it's the variance of the Monte Carlo estimate. Yeah, the central limit theorem also applies to this. And that's kind of why we're using this 1.96 business here. Okay, and so this. All right, so yeah, this is just a simple Monte Carlo integration, and it works, but there are some limitations here, and that is if we look at this at the function itself. Okay. If the function is not uniform, okay, and this one's not, obviously, but especially if there's only certain locations of the function that have values, and everywhere else it's kind of close to 0 or something like that, which is often the case in high-dimensional areas. Doing uniform sampling across the whole space is not an efficient way to go, because most of the time, if there's only a few locations where the function takes on values, most of the time when you take a uniform sample, when you evaluate the function, you get something close to 0. Okay, and so if one person does a sample and another person does a sample, if your sample size is not relatively huge, and one person just gets a whole bunch of zeros, their evaluation of the thing is going to be quite low, and then the other person might have gotten lucky and hit kind of the target zone a few more times, and so their estimate's going to be quite different. So this uniform sampling may not be a good strategy. Okay, so uniform sampling may not be a good strategy, especially if the function, has only a few locations of interest. Okay, so you can imagine, especially in high-dimensional space, but if it's like, your function looks kind of like this, where you just have a location here and a location here, where there's values, and these are supposed to be close to 0. Okay, then then, you know, depending on where you've drawn your samples, right? So if I'm drawing stuff over here, all of these things, all of these samples, these all get evaluated to 0. It's kind of just like wasted samples and calculations in here. Okay, really, what we want to do is we want to probably try to sample this part. We should sample this part and this part. These are the parts we want. Parts to focus on. Okay, and so, you know, we can focus on these areas and get a good sense of what these are. But then, you know, obviously we would no longer just take a simple average of these things, because we've oversampled this part, and then to say that, you know, everything is weighted the same, that would not be a good way to go. Okay, and so that's kind of the topic of importance sampling. We set certain areas to be more important, and then when we do the calculations accordingly, to compensate for the areas that we've stressed versus did not find as important. Okay, yeah.
Is there like a quantitative measure of importance that you've used?
Yeah, it's not. We try to find simple distributions, like distributions that are easy to sample from, to that will kind of highlight the important areas for us. Okay.
So in a sense, it's like rejection sampling.
It's there is a parallel thought, but it is different. So, but yeah, we'll spend Friday talking about it. Okay. But so today I've showed you kind of the uniform case, where we just say we're going to just randomly sample across the board without discrimination, and then and take the average to get at it. Okay, and then we'll expand on that with importance sampling.